Welcome to this explainer on flow control in pipelines. Today, we're going to rigorously unpack the mathematical modeling and actuation strategies used in the industry right now. This comprehensive curriculum, it was meticulously prepared by Dr. Nima Madian. And we're going to approach this topic just like an experienced engineering professor would. Giving you those intuitive explanations, the practical industrial examples, and of course, the clear mathematical derivations you absolutely need to truly master pipeline flow control. Here's our agenda for this session. 1. The Industrial Flow Challenge. 2. Valve Control and Nonlinear Physics. 3. Linearization and System Gains. 4. Transport Delay and System Synthesis. 5. Pump Control and Booster Stations. And finally, 6. Comparing Flow Actuation Strategies. Let's dive right in.
Section 1. The Industrial Flow Challenge. So, before we get into the heavy math, we really need to understand the physical reality on the ground.
Our foundational subject relies on massive physical transmission lines that literally keep global industry moving. When we talk about flow control, we aren't just talking about, a tiny pipe in a chemistry lab. We're looking at massive, highly engineered, heavy-duty industrial infrastructure.
Now, what's truly staggering here is the sheer scale we're dealing with. We have over 23,000 kilometers of oil and gas pipelines currently installed, and that network is always expanding. To put that into perspective, the core objective is deceptively simple: just maintain a constant flow rate. But the fluid has to overcome some severe natural obstacles. You've got the elevation head, that's gravity pulling the fluid down as it travels up mountains and across valleys, and then the friction head, which is this constant energy-draining drag of the fluid right against the pipe walls. To regulate this whole shebang, we rely on two primary interventions: control valves, which act as a variable resistance, and specific pumps, which actively add energy into the system.
Section 2. Valve Control and Nonlinear Physics. To actually conquer these physical obstacles, we have to understand our very first actuation strategy. Just like in standard manufacturing processes, a control valve regulates output flow by acting as a sort of generalized orifice. It provides a variable physical resistance to the flow, mathematically denoted here as R of X, where X is the actual physical displacement of the valve stem. As the controller observes the flow, it adjusts that valve position, X, to match our desired flow set point. It's a really beautiful bridge between fluid mechanics and closed-loop control.
So, check out this core nonlinear fluid dynamics equation. This mathematically defines exactly how our output flow behaves out there in the real world. The output flow rate, F sub O, equals 1 over the valve resistance, R of X, multiplied by the square root of a rather complex term. Inside that square root, we're looking at 2 times gravity times the elevation difference plus 2 times the total pressure difference, all divided by the fluid density. And honestly, it's that square root right there that makes this system highly nonlinear and mathematically, well, a real headache to control.
Let's break down these independent variables clearly from an engineering perspective. Our output flow rate is naturally a function of 3 independent environmental variables. First, the valve's displacement, X, which we can actually control. Second, the total pressure difference across the line, delta P. And third, the elevation difference, delta H, which is just caused by natural surface variations. If any single one of these 3 variables shifts, our output flow changes with it.
Section 3. Linearization and System Gains. Because nonlinear equations with square roots are notoriously difficult to control using standard PID controllers, we've got to transition to our next critical step.
To tame that wild nonlinear physics equation for our control systems, we basically expand the original function around a specific operating point using a Taylor series expansion. In step 1, we take the partial derivatives of the flow with respect to each of our 3 independent variables: the elevation, the pressure, and the valve displacement.
By first applying those partial derivatives, and then executing a Jacobian substitution, which, by the way, we derive directly from the slopes of the control valve's characteristic performance curves, we successfully nail down our constant system gains. We label these constant gains alpha, beta, and gamma. So now, instead of a messy square root, we get this clean, linear equation: the change in flow equals alpha times the change in elevation, plus beta times the change in pressure, plus gamma times the change in valve position. Honestly, this is a massive mathematical victory for our control architecture.
Section 4. Transport Delay and System Synthesis. With our linear gains mathematically locked in, we now have to address the most critical, and frankly often the most frustrating, dynamic factor in any long-distance transmission line. The physical reality of a pipeline is that a command issued at the valve at point A does not instantly alter the flow miles away at point B. The fluid has a specific velocity, v, traveling over a total distance, L. This creates a delay time parameter, tau, which simply equals L divided by v. In our control system, this physical transport delay is mathematically modeled using a Laplace transfer function, g equals e to the power of negative tau times s. And a quick warning, if you ignore this delay in your math, your real-world pipeline is going to oscillate wildly out of control.
Let's see how all of this builds into our complete system block diagram, effectively unifying our linearized physics with the pipeline's inherent dynamic delay. This right here is the synthesis of everything we've learned so far, presented exactly as you'd see it in a professional engineering schematic.
Notice the elegant flow of this diagram. Over on the left, we have our desired flow set point. The air feeds right into the controller, which outputs a change in valve position, delta x. This delta x is then multiplied by our gamma gain. Meanwhile, disturbances from pressure, that's our beta gain, and elevation, our alpha gain, are summed together. Finally, this entire physical interaction is subjected to the e to the negative tau s transport delay block before it becomes our actual observed output flow. It just beautifully and mathematically closes the loop.
Section 5, Pump Control and Booster Stations. Having thoroughly mastered valve throttling and its associated math, we're now shifting our focus to our second major architectural approach.
Here's the thing. Throttling a valve restricts flow, which inherently wastes some energy. Rather than doing that at the destination, this inlet pump configuration actively injects energy right at the source, for example, directly at the oil well. We use a standard architecture here. A constant speed pump, labeled P1, operates continuously just to establish our baseline nominal flow. Then, a secondary variable speed pump, P2, is linked to the controller to dynamically fine-tune the exact required flow. It is an incredibly efficient way to match supply with demand.
However, for vast geographical distances, remember those 23,000 kilometers we discussed earlier? Inlet pressure alone simply cannot overcome the cumulative frictional losses. The fluid would literally just stop moving. This makes strategically placed midline booster stations, utilizing these really powerful turbine pumps, an absolute physical necessity. Engineers actually calculate the exact count and placement of these stations based on total length, capacity, and that continuous friction. Looking closely at this inline pump control architecture, notice a major shift here. Unlike valve-based systems where we manipulate a physical restriction, here our primary controllable variable shifts entirely to the pump speed, denoted as N. But what's really fascinating from a mathematical modeling standpoint is that we still utilize the exact identical partial derivative linearization principles we learned earlier. And just like valve control, the dynamic lag, our tau parameter, must absolutely be incorporated into the pump control loop design.
Section 6, Comparing Flow Actuation Strategies. To conclude our academic journey today, let's bring all of these complex concepts together.
By placing these two engineering methods side by side, we can clearly visualize the conceptual bridge we've crossed today. On the left, we're regulating output via physical resistance at the destination point, while on the right, we're actively adding precise amounts of energy at the source. Both achieve flow control, for sure, but through vastly different energetic and physical means. Bringing everything together into a final synthesis, we can map out the fundamental physical characteristics right next to each other. For valve control, your primary variable is valve displacement, x, and it relies on Jacobian slope gains. Plus, it's typically located at delivery or outlet points. For pump control, on the other hand, your primary variable is motor speed, n, utilizing a paired constant and variable speed configuration. And you'll typically find this at the source or at midline stations.
Ultimately, whether you design a system to throttle with valves or boost with highly engineered pumps, your design absolutely must mathematically account for the universal governing constraint of physical transport delay, tau equals L over V. Understanding this connects the pure physics of fluid dynamics directly to the precision of modern industrial control systems, leaving us with a profound appreciation for applied mathematics. So, armed with these rigorous linearization techniques and architectural strategies, what real-world engineering challenge are you going to solve next?